and it automatically creates a static simulation for me. All the loads were applied based on the joint locations and the load-bearing faces that we define in our mates. And we're just applying forces, and this type of model is going to use inertial relief to balance the linkage. So we have 3 pivots in here, and it would be hard to fixture this part without creating abnormal stresses. So we don't need any fixtures. The loads and forces will balance, and any kind of the numerical error remainders will be balanced out with this inertial relief capability. So now I have a von Mises stress plot, which is what we're all very used to looking at. And we have many ways to view our stresses and discern what's going on in the model. Here I can use iso clipping to show stresses above and below specific values. I can cut through the model with section clipping to walk through our part. And we can look at displacements and strains. And then what's nice, especially if we have multiple materials in the model, is we can look at factors of safety. So this is going to divide the stresses at a location by the strength of the material with respect to yield if we're doing a linear analysis, and give us a factor of safety. So we've got a minimum factor of safety of 10 here, which is pretty high. Aero tends to be a little lower because we need to get into the air. And anytime we're viewing any type of plot in all of our simulation tools, we can go ahead and pick values at specific locations and then view them relative to each other. So we can see our factor of safety is going from 129 as we walk across our fillets down to 25 or so where I've picked. Now, if I want to save these locations, I can just say save this as a sensor. So the next time I look at another plot, I can recall those locations. So now let's look at our stress values at those specific spots. I can go back to probe and say from sensors, and it automatically remembers those locations. Very handy tool. Now, what about repeated loading? So we have a quick and dirty fatigue check built into static analysis for simulation professional. And this is here at the bottom. And when we create a fatigue check plot, it's essentially evaluating our part for infinite life and saying, you know, do you need to do a more in-depth fatigue study, or are you good to go? So surface finish is going to affect your fatigue life and is part of our fatigue adjustment parameters. So let's assume this is a ground finish, so a pretty decent surface finish. If it was something like hot rolled with a really lots of nooks and crannies in the surface, you can see that our strength reduction factor is going to be higher. We're going to reduce the strength more, so this number becomes smaller. In addition, the type of loading, this is mainly a bending type of load. And then there's a size factor. The larger your parts, the statistical probability of having inclusions or defects in the material is going to be higher. And it's saying right now, your stresses are so low, they're far below yield, our factor of safety is 10, it's not going to be an issue. But of course, we're doing a demo here, so I at least want to show you what the full fatigue tool would look like. And as we're going to learn, this is not going to be our worst case load. So when we look at a completed fatigue study, the outputs from fatigue are going to be the number of cycles that we can survive in addition to the level of damage. In this model, we're showing damage levels over 100%. 100% damage equals a high probability of surface cracking. And what is the input to my fatigue study? That's going to be my static analysis, defined as an event. And we can add up multiple events because usually, as we see, a part does not just survive through a single loading type. But we'll start out with just our linear static analysis from our harsh landing. We're going to say we want to go for 1 million cycles and assume that the load is fully reversed. In fatigue, compression actually helps. So that's why we need to define, is it fully reversed? Is it a mean stress of 0? Or are we going to be zero-based, apply the load and remove it? Or is it some ratio in between? Now, because our loads were so low, I bumped up the scale of the analysis, because this is coming from a linear study, to a factor of 20. If I put this down to a 1, we would see that our damage is essentially 0 in this part because we're substantially below yield. Now, based on this load case, I can start removing material from this part. And that's where the optimization tool comes in. In SOLIDWORKS simulation, we can create parameters from our model that we're going to vary. These parameters can be feature parameters in our model or sketch dimensions. And all we have to do is display our parameters and pick them, and we see that they're linked. And now this is something that we can vary in our design studies or our design optimizations. In addition, load inputs can become parameters. Anytime you see a pull down in SOLIDWORKS simulation, we can make these values that are inputs to the sim a variable. For example, rotational velocity for a centrifugal problem, or the magnitude of a force or displacement that we're enforcing on our model. They can become variables, and we can use our multi-run tools to run multiple simulations with one click. In this case, I want to lighten this up. So I created a couple sketches and some extruded cuts in here to lighten the model. And we're going to take a look at a design study that was created. The inputs to this model are the depth of cut. So when we look at this, as we walk through, I have a cutout on the top and the bottom, in the middle of the linkage. And we're starting out with a minimal or zero cutout, 5 millimeters, 10 millimeters, and 15 millimeters. Now, my constraints, these can be any one of our sensors that we create in SOLIDWORKS simulation. And right now we have a sensor tracking mass, and then we have another sensor that's tracking the maximum stress in the model. So we say that this stress must be less than 25 megapascals for this particular scenario, and minimize the mass. From there, SOLIDWORKS will automatically rerun each of our simulations. And as we see, all of our scenarios passed the stress test, and our optimal is the one with the least amount of mass. So 1,956 grams versus 1,600. So a 30 gram mass reduction in our individual linkage. And we can view our stress plots as we walk across each one of these scenarios. And then we can also create response graphs. In this case, looking at our stress across our scenarios. So we see we went from the 8 megapascals up to 11 megapascals, still well below our limit. And then in a real-world scenario, we would want to take this model in our idealized situation, so at the 15 millimeters, go back and rerun this stress study, and then double check our fatigue life once again. But we can get a good feel for the level of stress here. Fatigue should not be an issue. Now when we add this with other load cases, that could be a different story.